Hello and welcome to In Simple Terms with Satish. It is 2 in the morning inside a factory. A conveyor motor is still running. There is no smoke, no warning light, and no obvious breakdown. But something has changed. Its vibration is slowly rising. Its temperature is slightly higher. And the electrical current no longer looks as smooth as it did last week. The machine has not failed yet, but its digital twin may already see the failure beginning. A digital twin is a virtual representation of a real machine or system that stays synchronized with the physical world. That last part matters. A normal 3D model shows what a motor looks like. A dashboard shows its latest numbers. A digital twin tries to represent what this specific motor is doing now, why it is behaving that way, and what may happen next. The system begins with sensors. An accelerometer measures vibration. A temperature sensor watches heat. Electrical measurements track current and voltage. Other machines may add pressure, flow, speed, sound, or lubricant data. Those measurements need timestamps and the correct machine identity. Then an edge gateway or industrial controller collects them and sends them into a time series data pipeline. Now the virtual model receives a live pulse from the real machine. But data alone is not a twin. The model also needs context. The motor design, safe operating limits, current load, production speed, maintenance history, and relationships with nearby equipment. That context prevents a common mistake. Higher vibration does not always mean failure. A machine running faster or carrying a heavier load may naturally vibrate more. The twin asks a better question. Is this behavior normal for this machine under these conditions? Imagine an illustrative example. At its usual load, a motor normally vibrates around 2 millimeters per second. Over several days, it rises to 3.2. Its temperature also climbs from 68 to 78 degrees Celsius. Neither number alone proves that a bearing will fail, but together, under the same load, they form a changing pattern. A physics model may estimate how friction and heat should behave. A machine learning model may compare the pattern with previous bearing failures. The difference between expected behavior and measured behavior is called a residual. When that residual keeps growing, the system can flag an anomaly. The next step is not simply saying the machine is broken. The useful output is a decision. Keep operating, inspect soon, reduce the load, or schedule maintenance before the next production run. Some systems also estimate remaining useful life. That might mean the bearing is likely to remain usable for days or weeks, not that it will fail at an exact minute. The estimate should include uncertainty. Then, the prediction enters the maintenance workflow. A work order is created, a technician checks the machine, the bearing is replaced, or the technician discovers that the sensor was loose. That result must return to the twin. Without repair outcomes and false alarm feedback, the model cannot learn whether its prediction was useful. This is why digital twins are becoming an important industrial topic. Samsung has announced plans to use digital twin simulations, AI agents, and predictive maintenance across its manufacturing operations. Siemens is bringing real-time engineering data, simulation, and factory models together through its digital twin composer. The direction is clear. Factories want to test changes and detect problems in software before paying for them in the physical world. But a digital twin is not magic. Sensors drift. Models become stale after machines are modified. Rare failures may have little training data, and too many false alarms teach technicians to ignore the system. So engineers must validate the model, quantify uncertainty, monitor data quality, and keep humans inside important maintenance decisions. The mental model is this. A digital twin is a living engineering shadow. It watches the real machine, remembers how it normally behaves, compares reality with expectation, and rehearses possible futures. Predictive maintenance is not about knowing the future perfectly. It is about noticing weak signals early enough to choose a cheaper and safer future. If this helped you understand the topic in simple terms, follow or subscribe to In Simple Terms with Satish and share this episode with one friend who likes technology. I will see you in the next episode.